Good morning, everyone, also from my side. Good that you're here already at, 9:30. It's my great pleasure to introduce to you our first speaker of this morning, Daniel Greenberger, who has been a professor of the City College of New York for a very long time, and has also had visiting professorships at Oxford, MIT, and Berkeley. He's well known for his foundational contributions to quantum information. Probably most well known are the GHZ experiments, where GHZ stands for Greenberger, Horne, and Zeilinger. And I can believe that he might tell us more about this. And in particular, his contribution or invention of three-partite entanglement. And without any further ado, I'd like to welcome Daniel Greenberger to the stage. We might need to set up the overhead projector a little bit.
Mm-hmm. I thought it might turn it into Dovedawa. Okay. The field of quantum foundations just in the last, not only few weeks, but within the last year, has lost two people who really affected the field very, very strongly. And they were both very dear friends of mine. And so I'd like to say a little about each of them. And one is Helmut Rauch, who invented the neutron interferometer. And the neutron interferometer really made a tremendous difference in foundational problems, because it suddenly allowed all these Gedanken experiments that nobody thought could ever be done. It allowed them to be done. And so Professor Rauch, who trained many, many students in the field, was he was directly involved in many, many of these experiments. And so it's a big loss, to have lost him. He's a very original thinker, and he's one of that group of experimentalists who also are very deep theorists. And the same is true of a number of his students. Anton Zeilinger was one of his students, and he actually had many, many others. Anyway, the title of the talk is Thoughts about Entanglement and Other Topics, since most of the talk is going to be on other topics. And but one of the things about Rauch is it's a very good example of how serendipity affects the history of the subject. And so I'll give you a couple of anecdotes about some of the tremendous luck that went into, even after the careful effort of getting the neutron interferometer, of making it real. And the first of these was told at his funeral by Professor Bernadette, who was a student of his and has since gone on to become well known in his own right. And I wasn't at the funeral, unfortunately. They told me he had died, but nobody told me they're about to have a funeral. I guess they figured I wouldn't come all the way from the States, but I would have done that for Professor Rauch. because I really, as a person, I really loved him and his wife. But here's just a picture of the neutron interferometer. What it is there a laser pointer or something? Now, the interferometer, it's just a single crystal of pure silicon. And so that the atoms here are lined up with the atoms here. It's just a very carefully built single crystal, and that the manufacturers use it to make integrated circuits. They just, with a microtome, they just slice off very thin slices from this silicon crystal, and the physicists talked them into presenting them with a few of them. And the first thing, and so here's the way it works anyway. This is a single crystal of silicon, and there are these three sort of walls, and the neutron comes in, it splits, and gets recombined. And where at the x's is where you do an experiment, like if you put a piece of glass there, it'll slow the neutrons on one side relative to the other. And the way you tell that is the percentage of particles that go to D2 relative to D1 changes as you change the phase of one side. And so that's how you get the neutron interference. And a number of tremendous experiments have been done that way. I'll just mention one without going into details. But but for example, it was used to show that if you take a fermion and rotate it by 360 degrees, it goes into minus itself. And so that, of course, has been known for a long time, the property of fermions, but people didn't think it would be possible to prove it. And but what you do is you split the neutron, and so half of it's on this side, and you put a magnetic field on, and you rotate it by exactly 360 degrees. And when you come here, if all the particles have been going into D1, they'll now all go into D2. So you can tell that you've shifted the phase by 180 degrees. So that's for an example of a fantastic experiment with the interferometer. Now, they told, before the interferometer was invented, the X-ray interferometer was invented, and it works sort of the same way. But it works partly through absorption of the photons in the X-ray interferometer, whereas they only get scattered. In the neutron case, nothing gets absorbed. And so people thought it wouldn't work. And so they told Rauch that you couldn't build a neutron interferometer. So his answer was, well, let's try it. And so he put a couple of students to work for over a year in building the interferometer. You start with this perfect crystal, which has been given to you by the transistor people. And what you do is you have to carefully machine in a machine shop the device. And you have to be very, very careful because after all the atoms are lined up. It's a single crystal. And so that the atoms on one side have to be coherent with the atoms on the other side, or it won't work. And so after about a year or so of hard work, they had this device which was worth about $250,000. And one of them was telling me my salary at the time was the equivalent of $5,000 a year, and we were working with this very delicate device. And so they brought it to Professor Rauch, and he said, all right, set it up, and we'll see if it works. And one of the technicians while they were setting it up, dropped it. And it hit the floor and broke into a million pieces, the perfect crystal. And so they were afraid to tell Professor Rauch what had happened. But finally, they had to, and they thought he would kill them. But instead, he took it very philosophically, and he said, well, you'll have to make another one. So they got another crystal from the manufacturer, and they worked another year, and they had an interferometer, and they set it up, and they put the neutrons in, and sure enough, they saw fringes very quickly. And so that was how the interferometer there got built. So Rauch said, okay, great, make another one now, because other people will want them. So they started again, they made another one. And when it was finished, they tested it, and it didn't work. They couldn't, there were no fringes, they couldn't possibly get any coherence out of it. So he said, well, make another one. So again, they set it up, and they made another one. And again, it didn't have any fringes. So they thought, this is very funny, let's call the manufacturer. So they called the manufacturer, and he said, well, let me look it up. And he said, yeah, he said, what happened was that the first one and the third one and the fourth one were made by a new technique. And only the second one was made by the old technique. And of course, that's the one that had worked. And the trouble is that the new technique, in order to make it more pliable, the silicon, it was sort of doped with carbon. And carbon is poison to neutrons. And so it made it impossible to make a neutron interferometer out of it. And so if they hadn't dropped the original, it never would have worked, and they probably would have given up on the experiment. So that's a pretty fantastic story. And another amazing story, which this was told to me by Professor Rauch himself, and he said that they made it work here at the nuclear reactor at the Institute, which is a small reactor. And so then they were invited to take it to Grenoble. At the ILL at Grenoble is one of the world's biggest reactors. And so, and it has a beam many, many, many times the beam intensity that you get here. So they set it up at Grenoble, and it wouldn't work. And so everybody laughed at them, And then they came back to Vienna with it, and they set it up, and it worked. And well, then they found ultimately that the way the ILL is constructed, it couldn't possibly work. And that is, there's the big nuclear reactor in the center, and in order to be able to take out the neutron beams, the building is constructed with these long slabs going out in different directions, and each slab is a section of the laboratory. And because of the long slabs, they're supported on one end and not on the other end, and they have tremendous vibration. So that the labs at Grenoble have tremendous vibration, which doesn't affect nucleon scattering or so, but for coherent neutrons, it's impossible. It completely, if the thing can move by one atomic length, it'll wipe out the interference. So they couldn't get any effect at Grenoble until they learned how to build these completely damped structures that would wipe out the vibrations. So had they gone to Grenoble to use the machine first, it wouldn't have worked. And they had to do it at Vienna. And so the neutron interferometer, its success depends on a number of fantastic bits of serendipity. And so anyway, Rauch was a real hero in the field and really did change the history of the field. And but one of the problems of reaching my age is that all your friends are dying on you, and so it's no fun to reach such an age that everybody's passing away. But as Winston Churchill said, consider the alternative. And but one of the problems when these people die, they leave a big hole in your being. And one of the others who died this year was Mike Horne. And Mike Horne is sort of an unsung hero. He never got awards. He never got really notice or anything. And part of it was because of his own very humble personality. He was always self-deprecating and very modest. And yet, for example, without the CH-SH inequality, no experiments, or very few experiments, could ever have been done with the Bell theorem type experiments. And he did many other things. He was the chief calculator for Cliff Shull, and who was the Goyen of neutron experiments. And also, he was part of the GHZ states, the Greenberger, Horne, and Seilinger theorem, and which was a tremendous improvement on Bell's theorem. And it got the statistics out of it. It wasn't a probability of things happening. It was an amplitude for something either happening or not happening. I'll say more about that in a minute. And so let's see, that's... And a simple and very beautiful model of the GHZ states to talk about is David Merman's model of it. And he was also, I guess he's retired. He was also a great contributor. And, whoops. So now the Merman model is the following. It's a 3-electron state. And so you have 3 commuting operators, A, B, and C. And what they are, they're the spin. For particle 1, it's sigma in the y direction. For particle 2, in the y direction, and 3 in the x direction. And then the operator B, x is in the, for particle 2. And for particle C, x is particle 1. And so each of these 3 operators commute, so you should be able to measure them all simultaneously, which is very difficult to do. It has actually been done with photons. In Seilinger's lab, they did a beautiful experiment creating a GHZ state. But so here if you have a source that sends out the 3 particles, and so you can measure A or B or C in them, and they commute. AB equals BA, which you can just simply check out. And so you have a coherent state of the 3 different particles. Now, there's also a 4th operator, which is the 3 x parts, and it commutes with all of them. So you have 4 commuting operators, and they're not independent. The product A, B, C, D equals -1. So if you have 3 of them, you can you can get the fourth. And so now classically, so you can construct the operator A, B, C, D. Classically, if you have A, let's say sigma 1 y, if you measure it, it could be plus or minus 1. So it has a value m y1, which can be plus or minus 1, etc. So A, B, C, D has then the eigenvalues my1, my2, and mx3 for the 3. And then state B is yxy, and state C is xyy, and then finally state D is xxx. Now the product, they all commute, so you should be able to measure them all at the same time, and the product is minus 1. And if you look at what you would expect classically, if you take this product, each operator appears twice. my1, my1, my2, my2, and so on. So if each of the 6 products appears twice, so whether it's plus or minus 1, the product is always plus 1. So classically, the product of these states is plus 1, and there's no ambiguity about it. And quantum mechanically, the product is minus 1. And so classically, you get the wrong answer. And regardless of how you do it or how you do an experiment with it, you get the wrong answer. So a lot of people have said, well, instead of being statistical, like the Bell theorem, you only have to do one experiment. And so, but if you believe quantum mechanics is right, you don't have to do any experiment, okay? Classical physics contradicts the result of the GHZ theorem. And so the very fact that it exists, if quantum mechanics is right, then the classical description is wrong. And so it's a refutation of essentially Einstein's Einstein's definition of reality, which is if you can do an experiment as one spot and determine something elsewhere without touching it, then that something must be an element of reality because you've determined it and you haven't in any way interfered with it. And so it must have been there independently of the experiment you did because you haven't done anything to change it. And so it's a refutation of the idea of a classical kind of reality in that sense. There are lots of senses of reality, but it's very beautiful. And the fact it depends on the non-commuting sigmas sort of makes it extra beautiful that it's the commutation rules and the entanglement of the states that make it work. The operators A, B, C, as I say, have their is there chalk? The eigenstates, there are 8 eigenstates. I'll just draw 1 over the square root of 2, up for 1, up for 2, up for 3, minus down for 1, down for 2, down for 3. This is an eigenstate. And the other 8, for just an example for 1, here, if you just do this, plus or minus, doesn't down for 1, up for 2, down for 3, and so on. So there are eight of these states that you can construct, and those are the 8 eigenstates. simultaneous eigenstates of all of them. And so, and so it's a really very, very beautiful theorem. Now, Mike Horne and I, there were many, we met in 1978 at Grenoble, in fact. I had written a paper with Overhauser on the neutron interferometer, and that was the first. I had been originally a high-energy physicist and got interested in gravity and neutrons. And so anyway, I ended up writing a paper with Overhauser, and which explained the neutron interferometer. And he got invited to come to Grenoble. There was a very big meeting of all the people working with neutrons. And so he got invited and couldn't come, so he called me and said, why don't you go in my stead? And the MIT group with Cliff Schell and Mike Horne and Anton Seilinger were there. And so I started talking with them. We hit it off wonderfully. And so I started coming up to MIT. And that was 1978. So we had a 40-year collaboration until Mike just died. And hopefully Anton and I will go on for a while. And so, but anyway, one of the topics that Mike was thoroughly fascinated by was the Aharonov-Bohm effect. And so he and I used to have endless discussions over various aspects of it. And so let me just very briefly say something about it. One of the things about the Aharonov-Bohm effect is it really shows that quantum mechanics is non-local. There are many, many discussions of the locality of quantum mechanics, but they all depend on the interpretation of the wave function and so on. And there are all kinds of questions that you can raise, and so there are arguments all over. But this is a different kind of non-locality, and it's very beautiful. And Mike was very intrigued. I won't talk about that. Mike was very intrigued about the classical picture of it, and how far you could get classically, and the difference between them. But let me just give you sort of one take on what's going on, and that is you build a solenoid. Here's a top view of the solenoid, and there's a magnetic field running through the solenoid, and now there's a famous theorem, Stokes' theorem, says A dot dl is equal to the integral of B dot ds, the flux coming through it is equal to the line integral of A going around it. And so if you make a path around it, the circular path, then the flux is B times pi r squared if the radius is a little r. And the line integral is 8 times 2 pi r. So that tells you A is proportional to r inside, and it goes around. And B comes out of the paper, and A goes around. They're perpendicular. Outside, B is non-zero only inside, so the flux is constant. So if you make a path outside, the flux is constant, and so ADL, again, looks like 2 pi r times L, so A goes as 1 over r. Oh, what did I mistake? That's a B r squared over 2r, that's an r, not a c, over little r. So A inside goes up a proportional to r, and goes down over 1 over r outside, and they're continuous. A is continuous right on the boundary where little r equals big R. So A exists everywhere, but B only exists inside the solenoid. B is non-zero inside the solenoid. And because of that, if you take an electron and split it with a beam splitter, and let 1/2 go around this way and 1/2 go around that way, it encompasses the flux. Now, so that the phase for particle 1 is the phase of particle 2 times e to the I times, I left out some constants, but e to the I times the flux is what's important. So psi 1 equals psi 2 times the flux. So what happens if there's no flux, if psi is 0, psi 1 equals psi 2. But if there is a B field, then what happens, psi 1 is not equal to psi 2 because they differ by a phase. Now, the phase is not represented very well here, but what happens is, because there's no forces, see, the interesting thing is there's no forces outside. And so neither beam has felt any force as it goes around the different sizes. And yet there's a shift in phase. And so what happens if you look at if you make up a wave packet here, then here's the wave packet. There's no shift in the wave. There's no shift in the envelope because there are no forces. But within the envelope, the phase shifts. And it shifts by e to the I times the flux. And that's been beautiful experiments have proven that. And so the question is, what's the significance? What does it mean? It sounds amazing that you can, with no force, you can get this phase shift. And so here's what it means. Imagine you had to put a little hole in the solenoid, and a tiny hole won't affect the field by very much. And so you split. So what you can do now is you can do this experiment. Psi 1, and instead of psi 2 or 0, what you do is you send the beam right through the middle. So there is a B field here while it's in the middle. And so what happens is there's no field here, but this one does feel, and the beam curves in a circular orbit, so it bends slightly inside. And when you get it here between 1 and 3, the phase difference is there's only half the flux here. So the phase difference is half the flux. So psi 1 will lead psi 3 by half the flux. And then you do another experiment with psi 3 and psi 2. And it's not symmetrical because the beam bends one way. So whereas it bends towards 1, it bends away from 2. And so 1 leads 3 by half the flux, and 2 leads 3 by another half flux. So psi 1 leads psi 2 by the full flux. And, oops, I don't know if I have that right. But anyway, this is true. So, so psi 1 leads psi 2 by the full flux. And the moral is the following, that psi, if you write h psi equals e psi, the Schrodinger equation, psi is aware of all the experiments that you can do with this particular Hamiltonian. The Hamiltonian describes the physical situation, and psi describes the solutions. And so even if you decide when you make a wave packet, if you decide only to use the ones in this region where there is no B field, okay, where there is no B field, nonetheless, if you look at all these plane waves that go through this, what happens is they're aware of the fact that there is a B field in here. And the phases here will be curved relative to the ones on the other side. And so even if you make side 2, you make a wave packet which, again, feels no fields or anything. Nonetheless, psi is aware that the phases on this side are different from the phases on that side because you could have gone through here, and you have to take into account the fact that there's a real field and there are real phases. And so, so even if you choose to do your experiment in a beam where B is 0, it's aware of the region inside where B isn't 0. So you have this total non-local awareness of the entire space, the phases through the entire space. And so what happens is you have this phase shift between 1 and 2, even though your particular experiment ignores the fact that there's a field. And so that's very beautiful. Mike was concerned, I won't go into the details, but Mike was concerned by, so what we've done is we've assumed you do the experiment with no field, and you do the experiment with a field, and there's a phase difference. Mike was concerned with the fact that to build up a phase, you have to add the magnetic field, and that's a time-changing magnetic field. And the time-changing magnetic field induces an electric field. And so while you're building up the field, you have an electric field running around. And so, and the effect that you get from that is exactly the quantum mechanical one. Nonetheless, once you build up the field, it stops. There's no mechanism in classical physics for keeping track of the entire history of what's going on. And it's the non-locality that makes it work. Now, some people talk about, oh, there's extra significance of the vector potential and so on in quantum mechanics and so on. You can make arguments like that, but they missed the beauty and the point of what's happening. And explanations that miss the beauty are third-rate explanations, even if they're true. They're true, but they're only true. They're not beautiful. And they're kind of second-class true. And the last thing I'll talk about, though, is entangled states. And I'll just say a few things about that. And entangled states, which are states, a state that, where you can't, a multi-particle state that you can't factor into products of the separate particles. And they're literally entangled. And now, but they've been with us ever since the beginning of quantum mechanics. And people have used them and so on in the properties, but they just weren't aware of them. It wasn't until EPR that people really became thoroughly aware of the meaning of entangled states. And their significance. See, for example, in the helium atom, you have 2 electrons, and so to the 0th order, there are 2 hydrogen atoms. But then there's the Coulomb interaction between the electrons, and there's the L dot S interaction. And if you take those into account, what happens is neither electron, come on, you beast. Neither electron has an orbital L or an S. And they only have total L, which is L1 plus L2, total S, which is S1 plus S2, and a total J, which is L plus S. So it's not a state of two particles combined. The helium atom doesn't consist of two electrons. It consists of a two-electron state. They're entangled. They lose all individuality. And entangled states lose all individuality. And it's the way you have to see them. That for example, in the Bell experiment, you have spin 0, and it splits into two states of spin 1/2. And because the total state has spin 0, here's the wave function, the singlet. And you see if one is up, if particle 1 is up, 2 will be down, and if 1 is down, 2 will be up. So neither particle has a definite spin. You can't ask what's the z component of particle 1. It doesn't exist. It could be up or down. But what you do know is there's a definite correlation. If 1 is up, 2 will be down, and if 1 is down, 2 will be up. So the correlation exists, but there's no individuality for the individual states. And so that's the great lesson, or one of the great lessons of entangled states. The individual particles have lost their individuality. And of course, there's all kinds of wonderful things that go on with entangled states, but I'm just going to describe for you one experiment because it's so beautiful. It was done by Len Mandel and his students at Rochester. And an article by GHC in Physics Today, we described this experiment as mind-boggling, and I'll explain to you why it really is mind-boggling. And here's the experiment. You take a photon. Anything you can do with electrons, you can do with photons and so on. And there's an analog. So you take a photon. Now, this depends on the existence of down conversion. Now, parametric down conversion is a fantastic tool for creating entangled states, entangled photons. And until it existed, making entangled photons was a real hellish job. So when you talk about the experiments of Aspect in the 80s and so on, it was an incredibly difficult experiment, and it went on a very slow rate. Whereas now you can do the experiment in an undergraduate lab. And in fact, at MIT, they do it, I think. And it's because of parametric down conversion. Now, what parametric down conversion does, it takes one photon, it goes into a nonlinear crystal, and what comes out is two photons of lower energy. And they're both coherent with each other. And depending on how you cut the crystal, they can both be horizontal or vertical, or one can be horizontal and the other vertical. And you get the coherent combination of the two. So today we can easily make coherent entangled photon states. And they have these wonderful properties, one of which I'll show you. So what happens is, you just take a photon and put it through a beam splitter. And part of it is A, and part of it is B. And each one goes through a nonlinear crystal and gets down converted. So A gets down converted into C and D, and B gets down converted into E and E prime. Now, so what happens is you then do an interference experiment here, where beam C gets reflected and then goes through another beam splitter, and B converts to E, and it goes through a beam splitter. And so you get here, or you could put another beam splitter here. I mean, you could put another detector here. And so here are these two pairs, and you would expect to get interference pattern at D. But it turns out you don't. And the reason you don't is because if you look at A, the one that goes here, it goes into D prime, and this is a transparent crystal, the down conversion. So it goes through and it comes out here as D prime. On the other hand, if this one is converted here, part is E and part is E prime. Now, if you put a detector here, you can tell as you move the detector, you can see, for this is D and E, and you can tell which of the two photons you're seeing. So if you're seeing D, you know the path. So it's called a which-way experiment, because you can tell which way the photon went, and you'll see no interference. If you pick up E, then again, you'll get no interference. But if you're very careful and you line up the crystal in such a way that D prime and E prime overlap, at the moment they overlap, you can't tell any longer which crystal, which way the beam went. Because if they overlap, you can't tell if it was this one or this one. And as a result, you get coherence, and then and as soon as they overlap, you see fringes. So when the two beams overlap, you see fringes. Now, you don't even need the detector E, because in principle, you can't tell which beam the down conversion took place in. Whether the initial photon went this way or went that way, you can't tell because they perfectly overlap. Now, the reason I call this experiment mind-boggling is because this photon E over here, which determines either which beam they were in or the fact that they're in a combination of both, it's not even in the circuit. This goes one way, this goes the other. So it's this photon and this photon that are interfering, and this one just goes its own merry way. And this one also goes its own merry way. And the only thing they do is overlap or not overlap. So you get interference if you don't have overlap. So if you can determine which way knowledge, 10 minutes to go? I'm almost finished. So if you get overlap, there's interference. If there's no overlap, there's no interference. And you determine this by monitoring somebody who isn't even in the experiment. And if that isn't mind-boggling, then you've got a mind that won't boggle. So anyway, I find it an absolutely amazing experiment. And now there are other features, which I won't go into. But the moral of the experiment, then, good experiments have morals. That's right. All good physics experiments can be found in Aesop's fables. The moral is, if in principle you can't tell which way into which way information that comes in one beam or the other, then the beams will interfere. Once, I'm sorry, if you can't tell, right, then the beams will interfere. If you can tell, then they won't. And so that's a major feature of interpreting quantum mechanics. And it's a major feature of entangled states. And let me just say, without going into it, that this is the secret of quantum computing. It's the secret of Schur's factoring lemma. And that circuit doesn't consist of individual electrons. It consists of a coherent mixture of entangled electrons. And they have no individuality, which is why they can interfere. So what you have is not an electron system. You have an electron system, n electrons, but none of them have individuality. And the same thing, quantum teleportation it depends on the same result. And all the and there are a lot of really amazing entanglement results, and they all depend on this very same feature of the fact that the entangled states have lost their individuality and are very, 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 very non-classical in nature. Okay, so that's all I wanted to say. So, yeah.
Okay, thank you very much, Daniel Greenberger, for this very nice and enlightening talk. So we have a few moments for questions, and well, afterwards, after the second part of this tandem, we have a half an hour discussion time. So for now, I would just ask for immediate clarification questions, and then postpone the longer questions for later.
Could you put back the transparency about...
I'm sorry,
could you put back the transparency of the last experiment, maybe the mind-boggling one? So I'd just like to comment and hear your opinion. Actually, what is most surprising for me, that even if you put the two output beams D prime and E prime together, they overlap, and only afterwards you block the beam D, which connects the two down conversion crystals, then you lose interference.
Yeah, there's a version of the experiment. I think there's lots of interesting features, but one is, we used to call it the finger experiment. And that is, if you stick your finger right here, you'll block this beam E, and the interference pattern goes away. And then the question is, how long does it take for it to go away? And at the time it takes, for the moment you stick your finger in, is the time it takes for the photon to travel from here to the detector. So it's a relativistic effect that depends on, you can't go faster than the speed of light in the experiment. And speaking of the speed of light, I promised Chris that I would say something I usually say to my students, because I believe that quantum mechanics is for young men, but you've got to be young in mind, not in body. your body gets old and falls apart, and quantum mechanics keeps you young to the extent that you have students who you can inspire. And if you're going to inspire your students, you have to do it by convincing them that all the limitations that they're told about in their graduate courses and so on can't be true. They just can't be true. And so I always say that I promise that your children will someday travel faster than the speed of light, and there are a couple of other things that I said that they could do, but I don't remember. And anyway, so the reason is obvious. It's because why in the world would God create a universe where he's created intelligent beings, and after many years of evolution, you get intelligent beings, and they're stuck in one little spot? What's the point? Why did he bother creating the rest of the universe if it wasn't there for us to explore and admire? And there's really no point in it. It's almost an oxymoron that he would create such a universe. So if you ask what kind of a moron is God, he's an oxymoron. And I can't conceive of it not being possible to communicate faster than light, and a whole bunch of other restrictions of that type. So, go to it, it's just a question. Now, the way Thomas Edison would have done, he would have tried sending a photon through every material and seen which one ended up faster than light. It's not a good way to do it. And, but someday we will. Look, we already know how to slow down light to 0 speed. There's no reason we can't speed it up. And again, it's not that relativity is wrong. It's that relativity is limited, like all of our theories. And there are generalizations of it, which we will discover if we keep looking with an open mind is what's necessary. So I encourage all students to respect what your elders teach you, but don't believe what your elders teach you. And because there's a whole infinite of worlds out there, and so on. And if restriction makes no sense logically, then it can't be true in the long run. It's just a lack of imagination that forbids us from seeing it. Remember when the 4-minute mile, there was a 30 or 40-year period when people came very close to running a 4-minute mile, and nobody could break through. And the instant was Bannister, John Bannister, who ran a 4-minute mile. Within 5 years, everybody was running a 4-minute mile. Now even high school students run a 4-minute mile, and it was thought to be essentially impossible. So, and that's the way barriers go. They're there to be broken. Okay, so anyway, that's my lesson for students.
Okay, thank you very much for this nice lesson. I would say we leave the rest of the questions that you might have for the discussion, and we have a coffee break now, I believe half an hour. So let's reconvene here at 11 for the second part of the first time of this day.